Alternating series test. We have this new test as of last Thursday. Let's try this full screen thing and see how it works. And the alternating series test, recall, it just had two pieces to it, so that makes it pretty concise. And the first piece of it is really something we've already done before. So the first piece of the alternating series test is to take the limit of a sub k. So this, in other contexts, was called the divergence test. We take the limit of a sub k, and if that limit is not 0, what's true about the series? So if the limit is not 0, it diverges. And now recall that with an alternating series, a sub k is this. So a sub k is everything except the switch when we are talking about an alternating series. So the limit of a sub k is the limit of k factorial over k to the k. That is an indeterminate form. Yeah?
I know the one before that, we just set that one up. Will we come back to it?
The alternating series?
Yeah, so the right above this one.
Oh, we didn't finish it?
No.
Oh, yeah. Good point. Yeah, well, let's finish. We'll do this one first, then we'll finish that one. Thank you for reminding me. I didn't even notice that when I was looking at it earlier. So this is an indeterminate form, but we can't use a derivative technique because we don't know how to differentiate factorials. So what is this limit going to be? Which one of these grows faster than the other?
Factorial.
The power tower grows faster than the factorial. The power tower is the fastest.
Sorry, I didn't see the k to the k.
K to the k,
I
yeah.
just saw k.
Yeah, so this is by growth rates. So the factorial function grows very fast, but the power tower is going to grow even faster. So that's all we can say by growth rates. We can't actually formally do it any other way at this point. And then the second step is that we want to show that the sequence is decreasing. So we want to show that as we go further out in the sequence, the terms are getting smaller. So that's the direction I'll always write it, because a sub k plus 1 is beyond a sub k. So I like to write it in the order that you're sort of visualizing your sequence. So we want to show that. So a sub k is k factorial divided by k to the k. And we don't know, but we want to show that if we add 1, we are going to get a smaller value. So that's what we want to show. We want to show that. Well, let's do a little bit of, before we do anything in terms of multiplying both sides by something, let's first notice that on the right-hand side, you could write this as k plus 1 multiplied by k factorial. Right? K plus 1 factorial is repeated multiplication by subsequently subtracting 1, subtracting 1, subtracting 1, 5, 4, 3, 2, 1. So you subtract 1 from one factor to get to the next. So k plus 1 factorial is k plus 1 times k minus 1 times k minus 2, etc. So we can think of that as k plus 1 times k factorial. Just like 6 factorial is the same thing as 6 times 5 factorial. Right? And we can drop that factorial wherever we want. We could make this 6 times 5 times 4 factorial, etc. That factorial symbol can shift depending on what you need it to do. And down here, we're going to write this as, with laws of exponents, k plus 1 times k plus 1 to the k. You can just peel 1 off. Let's see what happens when we peel 1 off there. So the first thing I notice is that the k plus 1s are going to cancel right here. I also notice that the k factorials are going to cancel. If we divide both sides by this positive number, k factorial, that's going to go away. Bless you. Okay? So now we're going to do our crisscross multiplication, cross multiply. So we're going to end up with a k plus 1 to the k on the left, and a k to the k on the right. And then we can take the kth root of both sides. And we can subtract k from both sides, and we can always get down, most of the time, we can get down to an inequality with constants in it that we can solve by inspection. This is true. That's all the work for the alternating series test. Show that the limit is 0. Show that the sequence of terms is decreasing. Now we can make our conclusion. Therefore, we have convergence. So if those two things hold, if the limit is 0 and the sequence of terms is decreasing, the series must converge. Any questions? Daniel.
So the extra k plus 1 you got from the bottom is because the factorial?
This k plus 1 here?
Yeah.
That came from breaking this exponent apart. If you have this base raised to this sum, you can break it into the base to the k and the base to the 1 multiplied together. Because you add the exponents.
Gotcha.
It's like x to the 1 times x to the 2 is x to the 3, so we're separating it.
I forget, if something doesn't pass the alternating series test, is it inconclusive?
Yes, it's inconclusive. Right, not necessarily divergent. This here, if this is not 0 up here, you can conclude that the thing diverges. If the limit of a sub k is not 0, your series diverges instantly. But if that's true, but you can't show that this is decreasing, then it's just inconclusive. So if you had some oscillating function there, it would be inconclusive. Let's take a look at this one up here that we didn't quite finish last time. So let's see, where were we? So same idea. So the step 1 is to take the limit of a sub k, and a sub k again is everything except the switch. That's clearly 0 because the denominator is going to infinity, the numerator is a constant, so the fractions must be getting closer and closer to 0. And then the second step was to show that this is a decreasing sequence. So we found there's our a sub k, again, everything but the switch. Then we replace all the k's with k plus 1. So we have that. So that's where we're at. OK. So let's do cross multiplication here and just see what it looks like. So I'm going to move the lower right to the top left. So that's going to be, and actually I'm going to be a little more strategic. I'm just noticing something here. Let's do this. I'm going to put the logs on the right. So I'm going to kind of pair off the logs. I'm going to put these on the same side of the inequality. And I'm going to put the k's on the same side as well. So let's do it this way. I think this will be easier.
Is this an algebra trick?
Say again?
Is this an algebra trick?
It's an algebra technique for sure, yes. Like if you put everything on one side of the inequality, I'm just noticing that it's going to, I mean, it would still maybe work, but this I think will work better.
Okay.
Let's just notice this, that if we put the k's over here, excuse me, and we put the ln's over on this side, we would have that. And isn't it true that this is always greater than 1? K plus 1 over k? Right? It's going to be 1 plus 1 over k. And k is a positive integer. So that's always going to be bigger than 1. This is always going to be less than 1. Let's make sure we understand why. So here we could make this ln of k divided by ln of k plus 1 all quantity squared. Do you agree that I could rewrite it that way? If I pull out the square, we could square what's inside. And ln of k plus 1 is bigger than ln of k. So that means that this is a fraction that's less than 1, and if you square it, it's still less than 1. So if that side's bigger than 1 and this side's less than 1, that means this inequality has to be true, right? So therefore, this is true. So that's less than 1. And so therefore, we get convergence. So as long as both those things are true, the limit is 0, and this inequality holds. Usually we're not going to have to make kind of an argument like this. This is a little bit subtle, but when I started to move everything to one side, in my mind I was seeing, oh, k plus 1 over k is bigger than 1. I guess it would also work if we just moved everything to one side. In my mind I was thinking it could get a little messier, but if you do move everything to one side, we have the same setup. Let's see, that's going to be k, that's going to be ln squared. The only difference with the logic here is that we would say to ourselves, this part, that's bigger than 1, and this part is also bigger than 1, right? That's ln of k down there, ln squared of k. Isn't that part also bigger than 1? So if we take a number bigger than 1 and a number bigger than 1, if we multiply this over, we would have a 1 on the right. So from right here, we could also say that it's true. Either way, yeah. When I was imagining multiplying it all over, it looked a little messier, but it would work. Either way. Yeah?
I believe you also said on Thursday that we'd go back to the last question.
Mm-hmm. Yeah, we will get back to that. I want to get through the alternating series first, but then we will get back to that one for sure. For sure. Okay, so let's go to the remainder for an alternating series. And in math, when you're dealing with series, remainders are super important. Question?
Would you ever accept us plugging in values of k as an example?
No, because we have to do it in general, so it's got to be for all k. You can plug in values of k to get an idea, but if you just plug in a couple of values of k, that's not going to prove anything. So we're always trying to do it in generality so that it's true for all k, or for all k bigger than some specific k. Yeah, so we don't, but we can plug in values of k to get a sense. If you're not 100% sure what some sequence terms are looking like, you can plug them in to get a sense for sure. So in a lot of higher level math classes, you deal with these remainders for series and whatnot. You deal with estimations. And there's something called Taylor's remainder theorem, which you'll see in the next chapter. And it gets very tedious. And so dealing with remainders is something that we are not going to get super involved in if you go into a numerical analysis class. If you're going into certain engineering fields, you'll get to analyze remainders in great detail in the future. We are going to focus on one type of remainder, and that's for the alternating series because it's the easiest of all the remainders, and it's going to give us some insight into how remainders work. So let's take a look at the alternating series and try to understand how we can find an estimate for the remainder. So the first thing is that we are thinking of our series as two pieces. We've got the S sub n, and then we've got the remainder, which is what's left. So S sub n is the sum of the first n terms. R sub n is the tail, the corresponding tail. So if you look at S sub 5, you're adding up the first 5 terms. R sub 5 would be from term 6 to the end. Okay? So this is going to be, if you have a series that converges, that would be equal to the sum, the total sum. And so if you subtract, you can get an expression for the remainder. So the remainder is the difference between your nth partial sum and the actual sum of the series. So let's do a visualization here. So let's suppose we've got an alternating series that converges. So if that alternating series converges, let's suppose it converges to S. So S right here is the sum of the series. And let's suppose that S sub n is putting us right up here. So there's S sub n, whatever that y value is right there. That's S sub n. So when we add the next term in the series, which would be a sub n plus 1, that's got to take us down below s. Right? It's alternating. So you're adding, subtracting, adding, subtracting. So the next term is going to subtract and take us down to here. Right? So a sub n plus 1 is going to have a negative in front of it. The switch is going to be negative for it. So that's going to drop us down here. So we're going from there to there with a sub n plus 1. Okay? And then if we add the next possible term, would be a sub n plus 2, that would bounce us back above the dotted line again. And the next term after that would take us below. So you should be visualizing this oscillation around the sum of the series. Everyone okay with that? So if the alternating series converges, and that's our sum, each time we add another term, we're getting closer and closer and closer to that dotted line. So notice that this distance right here, so from here to here, that distance right there is a sub n plus 1. Right, that distance is a sub n plus 1. Now remember that for an alternating series, the a sub k doesn't include the switch. So there would be a switch, so there'd be a minus sign in front of it. But if we just think distance, a sub n plus 1 is that distance. The error, or the remainder, however you want to think about it, for s sub n is this distance right here, right? If this is s sub n, r sub n is going to be the difference between s and s sub n. It's going to be that distance right there. Agreed? All right, so s sub n, then you've got the remainder, and that gets you to s. So r sub n is the difference between s sub n and s. Isn't a sub n plus 1 greater? Isn't the red greater than the green? That's our key, is that the next term is going to be a reasonable estimate for the error. Obviously, the error is a little less than it, but that's a simple gauge on the error. Maybe you're not going to get the minimal error possible, but you can get a gauge on it pretty accurately. So all we need to do to get an estimate for the remainder is look at the first unused term. That's all we have to do. So let's do it. So that's all it's saying, is that we're going to look at the first unused term. Okay. So let's write out some terms here just to get a sense of what's going on, and I'll try to make it all make sense. So this series is going to be 1 minus 1/2 plus 1/3. So this is the alternating harmonic, which we've already said converges by the alternating series test. This is going to equal the natural log of 2. So what this means is the following. I'm going to put some words up here. So if we add up the first two terms, this is s sub 2. So r sub 2 would be the rest of this, which you could actually write as s minus s sub 2. Or you could subtract it. But here's how I want you to think of it. S sub 2, whatever that adds up to, in this case it adds up to 1/2. This is within 1/3 of natural log of 2. So the next term, which is the 1/3, the magnitude, we're always going to use the positive value for error. Okay? Now if we add the first three terms, s sub 3, oops, I wanted to change color. S sub 3 will be 1/2 plus 1/3, so that's 5/6, I believe. So that's s sub 3. That is within how much of natural log of 2?
1/4.
1/4. So if we add the first 3 terms, then we're going to look at the next term. The next term in this case, this is a sub 4. It's going to be within that amount of the actual sum, which is natural log of 2. So that's kind of how you want to be thinking about it. The magnitude of the next term is going to be our estimate for the remainder or for the error, however you want to visualize it in your mind. Okay, so now let's answer the question that was asked here. So if I go there, I guess if I want to get to my tools, I've got to come back here. There's that. Okay, so now let's go to the actual question. So the question here, this is just to get you a visualization of what's going on. Determine how many terms of the following convergent series must be summed to be sure that the remainder is less than 10 to the negative 4 in magnitude. Although you don't need to, the exact value of the series is given in each case. You don't need it. Okay, so we want to figure out how to make the next term less than 10 to the negative 4. So we want to add up a finite number of terms in such a way that the first unused term, the next term, is less than 10 to the negative 4. Okay? So if we can find the first term that's less than 10 to the negative 4, we want to add up everything that's in front of it. Right? So if we want the remainder to be less than 1/5, we're going to want to find the first term that has a magnitude less than 1/5, which would be 1/6. That would be the first one less than, strictly less than, not less than or equal to. But if we said, hey, we want to add up a finite number of terms so that the sum, that partial sum, is less than 1/6, or excuse me, less than 1/5 of the error, then we're going to come out and find the first term that's less than 1/5, which would be 1/6, add up everything in front of it, and then we would have a partial sum that is within 1/6 of natural log of 2. Okay? So we want to find the first term that's under 10 to the negative 10 to the negative 4. So we look at our term, 1 over k. We want it to be less than 10 to the negative 4, which is the same as this. 10 to the negative 4 is 1 over 10 to the 4. So if we can find the first k that's less than 10 to the negative 4, just add up everything in front of it. Let's see. So this cross multiply, and we get that k is greater than 10,000. So the first term that's greater than 10,000 is when k is
10,001.
10,001. So this implies that k is 10,001. And now this is pretty straightforward in the sense that we started counting at 1. So how many terms are in front? How many terms are we going to add up? This is going to be our error term. How many are we going to add up?
10,000.
10,000. So we're going to be adding up a sub 1 and then subtracting a sub 2. Let's just do this in generic terms. So here's our series. And then we get all the way out. Let's see. When we get to a sub 10,000, should it have a minus or a plus in front of it? Should the switch be minus or plus? Minus, because anytime we have an even index, so minus, and then plus a sub 10,001, plus, well, actually that one will be minus if we want to be precise. So there we go. We found that this term, a sub 10,001, this term is less than 10 to the negative 4. So what we want to do is add up everything in front. So we're going to add those. To indicate that mathematically, we are going to say You could write it out like this. So you could say we're going to add -1, k plus 1, whatever k. We're going to add from 1 to 10,000. That is going to be the sum of the first 10,000 terms. That is our answer. Will that work? There. We could also even just say add the first 10,000 terms. So we could also say it in words. And this is k equals 1. All right, let's try another one. Very, very visual, this stuff. So, same scenario. We want to have a remainder that's less than 10 to the -4. So if we can find the first term that's less than 10 to the -4, we just add everything in front of it. So we're going to come into our term, and we don't include the switch. We want this to be less than 10 to the -4, which is the same thing as 1 over 10 to the 4. 10 to the 4 is 10,000. We're going to cross multiply. We're going to isolate k. So we subtract 1, we get 9,999 divided by 2. So k is an integer. So what is the first k value that makes that true? If you divide 9999 by 2, what do you get?
7.5.
Say that again.
7.5.
Yep. What point? So what is the first integer that's bigger than that then?
5,000.
So 5,000 is going to be the first integer because that's going to be 4,900 something or other. So we're going to get 5,000. That's going to be the first integer that inequality is true for. So we want to take the first one. It's true if we chose a bigger one for sure, but we want the least number of terms that we can add together. Okay, so k, yeah.
It's kind of like a clarification
Sure.
question. So the remainder is like every single s of n value added up before like s of, or like 10,000 for this certain question.
Say that once again. I think what you said is right, but I want to hear it again.
So the remainder is basically every single s of n value added up before a certain like series number.
So the
Series value.
S sub n is going to be the sum of the leading terms.
Yes.
And then R sub n is the terms added together that are left, the tail. So there's no S sub n over here in the tail. So we're adding up, so if you look at the green,
Yeah.
the green is, this is S sub 3 if we add these first 3 terms together.
Yeah.
The remainder would be -1/4 plus a fifth minus a sixth plus a seventh minus an eighth plus a ninth. So R sub 3 is going to be everything from here to here. That will be R sub 3. And this first part of the remainder, that is going to be our estimate for the remainder. Our estimate for the, for the
So
remainder.
the remainder is everything from
S sub n on.
S sub n on
Yep.
to your S value.
Yep.
Okay.
So our leading terms contribute to the S sub whatever. So here's S sub 3. R sub 3 is the remainder associated with S sub 3, so it's going to be the sum of whatever's left. But an estimate for that infinite series right there is going to be the first term. Carter?
So how is this useful? Is this just some random thing?
Because whenever we have a series, we need to know how accurate it is. So when you're typing into your calculator cosine of 5 degrees. It has to provide an accuracy that fits in your calculator's window, right? So it needs to go far enough out in the series so that when it adds those numbers together and it displays a value, that value is accurate to what you need it to be. So when you're doing computations on your calculator, it needs to be accurate to whatever the numbers are you can see.
Okay, so we're finding out to, like, your calculator, for example, is finding out to like a certain digit what?
Yes, exactly. So
And does this go to infinity?
the remainder?
Yes.
The remainder goes to, yeah, the remainder is an infinite series.
Okay.
S sub 3 is finite, right? That's a finite series.
Are we always
So
gonna?
if you want less than 10 to the negative fourth, 10 to the negative fourth error, you have to calculate out to the 10,000th digit of this specific series.
We need to calculate out to the term that gives us less than 1 over 10,000.
Okay.
So as soon as one of these guys is under 1 over 10,000, then we add everything in front of it. So that's what we're trying to do, is to figure out, well, where is the first value of k that, what's the first value of k that meets this error threshold? 10 to the negative 4. On our calculator, it's probably going to be like 10 to the negative 10. Like they want it to be way small so that it fits in our calculator screen. The error's got to be tiny. Depends on what the function is, but.
And so what we were doing before is we were just finding out, like at infinity. So would we, on a different question, could we be asked like the remainder, like let's say if we had like a telescoping series, would we be asked like a remainder?
The only remainders we're going to deal with are with alternating series.
Okay, but
They're the simplest. But the concept is there. Any series that you can imagine, if you look at S sub 5,000 and you add up the first 5,000 terms, R sub 5,000 is the rest.
and you're trying, and what's so important about it is then, like let's say because we were at the like 1 over 10,000, so that means the number before it is like 1/10,000 off of
Yes.
the number?
Yeah. So like right here, this is we're 1/4 off or away or within of that. Down here where we're using the other, so here, right here, this term is less than 10 to the negative 4. So that means this finite sum in front, this S sub 10,000, is 10 to the negative, at most, 10 to the negative 4 off of the actual sum.
Okay.
So it's
Like off of the complete sum.
the complete sum, the original series all added together. Whatever that original series all adds together, we call it capital S. This partial sum, if we add up the first 10,000 terms, will be within that amount of the actual
You get pretty
S.
close to like the actual.
You can get very close, very fast with alternating series.
So you said calculators use this, so say your calculator goes to like 9 decimal places, so like a billion within
Yeah.
accuracy.
Right.
Does that mean that when you put in something complex, it'll do like the first billion terms of a series? essentially?
It means that whatever the computation is, it has to be accurate to, depends on whether we're looking at whole numbers or fractions, so it kind of depends on the function. Like if we think about a function like sine, where the value is always less than 1, then we're thinking about digits. How many digits can we go out past the decimal place and get accuracy? And so the calculator is going to use this thing called Taylor's remainder theorem to make sure that whatever is displayed on the screen is within whatever the screen width is. So if it's 10 to the negative 10, 10 to the negative 12, whatever. They'll go a couple digits further though, because we all know about compounding error, right? So as soon as you start rounding off a little too early, you're going to have some error. So they'll go a few digits beyond what they need, just to make sure that if you're raising things to powers, that you're not going to have some propagated error. But Taylor's remainder theorem will tell you when you can stop and get the accuracy that you need for your display. All right, so let's try this one here. This one's a little different because notice that it starts at 0 instead of 1. This one, where it started at 1, was pretty straightforward in the sense that as soon as we found the term that was less than 10 to the negative 4, oh, well, S sub 10,000, there's 10,000 terms because it started at 1. So here it's going to be a little different. So I think it's helpful to do a visual here. If you write out the terms, a sub 0 is going to be the first term. A sub 1, that's going to be a negative. So here would be a generic representation of what this series is going to expand, what the expansion will look like. And then we keep on trucking, and we get down to a sub, let's see. Let's go, I'm going to write out a couple of terms before. So let's do the one term before that. So a sub 4999, a sub 5000. Let's just do a few terms right here where we're kind of paying attention. The odds are negative, so this one should have a negative. The evens are positive. That should be a negative and then a positive. So there's what the terms look like, generic terms. And we found that when k is 5,000, that term, when k is 5,000, so here's where k is 5,000, right there. When k is 5,000, this is the first term that's less than 10 to the negative 4. When k is 5,000. So that means we want to add everything in front. We need to add those. How many terms are we adding together? 5,000. Because we have 4,999 terms when we started at 1, but then we have the a sub 0 term. So we have 5,000 terms. So we're going to add first 5,000 terms. So if we wanted to write this as a partial sum, we would say S sub 5,000. If we're going to add 5,000 terms, that's what this does. So this sum would be the sum of the first 5,000 terms. And if we're starting at 0, we're going to stop at 4,999. So that'll be the sum of the first 5,000 terms. That finite sum, adding up those 5,000 terms, is going to create an approximation to the actual sum of the series, which in this case is pi over 4. We will be within 10 to the negative 4 of pi over 4. We'll be super close. We'll be 1/10,000th away from pi over 4 at most. So overall, this is a pretty simple process because we only have to look at one term for our error estimate. We just look at the first term that we're not going to use as our error estimate. All right, any other questions on that one? All right, let's try another one. So, same concept here. So we want to be within 10 to the negative 4. We want the remainder to be less than 10 to the negative 4. We want so that essentially is saying we want the tail associated with our partial sum to have a value less than 10 to the negative 4. So let's try it. We want 1 over k squared less than 10 to the negative 4, so we want that. Right? A sub k doesn't include the switch. So there's a sub k. So we want to know, when is that less than 10 to the negative 4 first? When's the first time that's true? Okay, well, we do our cross multiplication. We need to take the square root here, and luckily enough, we can square root this really easily. So what does that tell us k is equal to? What's the first integer bigger than 100? 101. So that is our k value. Now we have to visualize what's happening here. So this says when k is 101, the error, or the remainder, is less than 10 to the negative 4. So we have to add everything in front of it. So we have to add from k equals 100 all the way down to k equals 1. So we're going to add from k equals 1 to k equals 100, so that'll be how many terms? 100 terms.
Will you do the visualization again?
Yes. So we're going to add the first 100 terms.
And that's an adequate answer as well.
Yeah. Yeah, that would be sufficient. So if we look at our visualization here for the terms, the first term, because our index value starts at 1, we are going to have an a sub 1. And when we plug in a 1, we get a positive for our switch. So when we're dealing with odds, we're going to have positives. When we bump to 2 and have an even k value, that's going to be odd on -1, so it's going to be minus. So this is what we're visualizing generically. And then when k is 101, so let's get a couple of k's around that just to make sure. So we're going to have minus a sub 100 plus a sub 101 minus a sub 102, etc. So the k value being 101, that's locking us in. When k is 101, we are right here. So this is the first term that is less than 10 to the negative 4. So we want to add everything in front of it. We want to add those. And because this started at 1, that means we have 100 terms. So if we're going to add from a sub 1 to a sub 100, that's going to be 100 terms. If this started at a sub 0, how many terms would we have? 101. What if it started at a sub 2? 99. Exactly. Yeah, doing a little visualization here helps to just sort of see, because it's really easy to be one off. And sometimes when you get this number k, that is the number of terms. Sometimes it's not. It all depends on whether it starts at 0 or 1 or something. All right, you all try this one. Same
So
thing.
basically, it's whatever the k value is minus your starting index. Is the number of terms that you get.
I think that actually is, yeah, I think that's true. Yeah, because if we start at 1, it's going to be exactly k if we start at 0. So yeah, that's right. Yeah.
Well, if you start at 1, then it's going to be k minus 1.
Let's look right here. So this is going to be that minus the 1. And yeah, we can look at the other page and see. I think that's true though. I think if you subtract out that initial index from your k value, that works first. Because if it starts at 0. Yeah, I think that's right.
If you follow that method, you'll never be one off.
Truth. Shouldn't be.
No excuses.
No excuses.
You can't say the sun was in your eyes this time.
No, there's no sun. So you might need a calculator to get an integer estimate of the third root of 10,000.
So we just find the
It's the very bottom, it's just the,
That?
yeah, it is that.
Oh,
It's
okay.
just a check off. So it looks like I have 2 minuses, but.
Yeah. we get k is 11. And then how many terms are you going to add together then if k is 11? Let's see. So this is going to start out as an a sub 0, and that a sub 0 is going to be positive. And then a sub 1, when that's an odd, that's going to be a negative. So this is going to be what the sequence looks like. And then let's straddle the 11. Let's get a sub 10, a sub 11, a sub 12. The evens are positive, so that's a positive, negative, negative, dot, dot, dot. So we found that when k is 11, let's see, here's where k is 11. That is the first term that's less than 10 to the negative 4. So we want to add everything in front. So we're going to add those. So add the first 11 terms. So there is, and if we wanted to write it out in sigma notation, we would be adding from k equals 0 to 10, right? K is 0, k is 1, all the way up to k is 10. So 0 to 10, this. And this would be S sub 11. S sub 11. S sub 11 means the sum of the first 11 terms. It doesn't mean stop when k is 11.
So can we write S sub 11 as our answer?
Yep, you could write S sub 11 as your answer because that means add the first 11 terms. Yep.
So you could do sigma notation S sub 11 or add for select.
Yep.
Okay.
All the things. Yeah. Daniel.
This is kind of more of a complicated question. If in the sigma, say there was a 3 instead of a 1 in the numerator there, can we
Mhm.
factor that 3 out to the front?
If there was a 3 like in here,
Where the
Up there?
Yeah, can we factor it out to the?
you could factor it out.
Okay, fine.
Yep, absolutely. I mean, the only thing you have to be careful with there that is if the 3 is in there, it's part of a sub k. Actually, it's better not to factor it out.
Okay.
It is true if you were going to find the total sum in the ones that we've seen, if you knew how to find the total sum. But for here, if there was a 3 here and you factored it out, then you're changing the magnitude of that term.
Okay.
So you want to leave that. You want to leave this as is.
Okay.
Yeah, you don't want to factor it out. Now that I think about it more carefully, you want to leave that whole thing intact when you set it up with this inequality.
Got it.
Yeah. Good question. All right, let's go to the classification of convergence for an alternating series. Okay, so I'm going to put the emphasis on a convergent alternating series. Oh, I don't want to actually highlight that right there. Let's just suppose that we have a convergent alternating series. So we've got half pluses, half minuses, and it converges. With an alternating series, you can classify that convergence in one of two ways. That convergence can be absolute or it can be conditional. So if we have a convergent alternating series, we've got half the pluses, half the minuses, mashing them all together gives us something finite. So we've got a convergent alternating series. That convergence is either absolute or conditional. And here's what that means. If you take the absolute value of every term, that is going to be absolute convergence. So, and that's what the word absolute is referring to, absolute value of every term. So absolute convergence, you've got your alternating series is converging, but then you change it and you take all positives. You make everything positive. You take the absolute value of every term. So if that thing converges, the original series is going to be said to converge absolutely. In other words, the minuses didn't matter. Like, we know a great example where the minuses matter, right? If we have this alternating series here, the alternating harmonic converges to natural log of 2. But if you take the absolute value of every term, you end up with the harmonic, which diverges. So the alternating harmonic will not converge absolutely. It will converge conditionally, because the series of absolute values diverges, but the series without the absolute values converges. Right? So that tells us that this series is conditionally convergent. Conditionally convergent is, you need the minuses. If you take away the minuses, it diverges. You need the minuses. The convergence is conditioned on having those minuses that keep the sum from inflating.
So do we always need to categorize an alternating series as one of these?
Mm-hmm. Yeah. So that's what it'll say on the test. It will say, show this alternating series converges, and then classify that convergence. And generally it's not hard. Usually it's pretty obvious, because most of the time we're dealing with p-series and things that you can analyze pretty easily. So first off, we have this theorem here that says, if the absolute values converge, well, then the series that has minuses must also converge. If you have a series of absolute values converging and you throw in some minuses, it's still going to converge, right? So if you have a series, positive numbers, but then you make some of them minuses, still going to converge.
So when it's like saying clear convergence, so then we do what we already learned with the alternating series, and then we do this next.
Yeah. So we do the alternating series test first, which will tell us that the series converges. And then we have to look at the series of absolute values and make a judgment on whether that converges or not, and then we make our conclusion. So if both the alternating and the absolute values converge, then it's going to be absolute convergence, and otherwise conditional.
Does this also mean that now, if we have an alternating series, instead of doing the alternating series test, if we can find that the absolute value of it converges, we can just say it converges?
Yep. That is 100% true. So because if the series of absolute values converges, then the series with the minuses also converges, you could, instead of doing the alternating series test, you could say, oh, the series of absolute values is, say, 1 over k squared. And I know that that converges because p is bigger than 1. So absolutely. Yes. So equivalently here, if we have a series that has minuses in it, so here there's no absolute value. If we've got a divergent series, so there's some minuses in there, if you force everything to be positive, that's still going to diverge, right? It's going to be even worse. Right? If you have pluses and minuses, and it diverges, and you turn all the minuses to plus, it's going to diverge even worse, if that's even a thing. Right? It's going to be super divergent, hyperdivergent.
Diverges faster.
Diverges faster. How fast does it mean to diverge? Okay, so let's try one of these. So here we've got alternating series. We see the switch. So determine whether the following series converges absolutely, conditionally, or it diverges. So do we need to, let's see, do we need to review p-series? Do we remember p-series? Let's put it over here on in the corner. So p-series is 1 over k to the p. And if p is bigger than 1, what do we get? We're going to get converges. And if p is less than or equal to 1, we get diverges. Okay, so that's p-series. So if we look at this and we see that, we know that that's going to converge or diverge. Diverge, right? That's going to diverge because p is 2/3 and that's less than 1. So we know that the series of absolute values is going to diverge. Keep that in our mind. So first, let's show that this actually converges. So we have two steps. We want to take the limit of a sub k as k goes to infinity. So the limit of a sub k is the limit of 1 over k to the 2/3. As k goes to infinity, that's 0, so that first step checks. So it doesn't diverge by the divergence test. And now if we can show that the sequence of terms is decreasing, so if we go further out in the sequence of terms, we want to have a smaller magnitude. So that's what we want to show. So if we want to show that, let's see, 1 over k to the 2/3, we want to show that that's bigger than 1 divided by k plus 1 to the 2/3. And this is pretty fast. We're going to cross multiply. We don't know, so I'm going to put question marks here. All right, everything's positive here. We don't have to worry about weird root things, so we can cube both sides and then take the square root of both sides. Everything's positive. So in other words, we can do this. And then subtract off k. This is true. So that checks. So that tells us that therefore we have a convergent series. So that's convergent. We have a convergent alternating series. So now we're trying to classify that convergence. So we have to consider the series of absolute values. There is the series of absolute values. Series of absolute values, you just get rid of the minus signs. And here's how we decide. First you identify P. Now I know you know it's a P series. Then you compare it to 1, and then you make your conclusion.
It's conditionally converging.
So their final conclusion, convergence is conditional. Yep. So if the series of absolute values diverges, the original series converges only conditionally. Must have the minuses. Because if you take away the minuses, you get divergence. So this is regular convergence, alternating series test. The alternating series test gives regular convergence. And then we test the series of absolute values. So this is the series of absolute values over here. Series of absolute values diverges. So then the original convergence is classified as conditional.
We don't have to add the counters to the summation.
The switch?
Yeah.
If you take absolute values, this goes away. Right, this is the series of absolute values.
I meant the k equals 1 of the infinity.
Oh, no, it doesn't matter.
Okay.
Because the first finite number terms don't matter.
Okay.
Right, yeah, you don't have to. Usually when we're trying to summarize, we don't write all that stuff down.
Okay.
Yeah, Harrison?
Why is it sometimes -1 to the k plus 1 and -1 to the k?
Usually it depends on what this index starts at. Usually they want the first term to be positive.
Okay.
But
So,
but it doesn't have to be. You could start with if the first term started out to be negative and it converged, it would end up converging to a negative number.
okay.
But usually they want the first term to be positive.
And this is gonna matter later?
No.
No, it just doesn't. So the positive and negatives, does it really matter right now?
I mean, it matters that they're alternating, that they're not like in some weird
Yeah.
triple negative and then triple positive or whatever.
Yeah, but we don't really need to worry about it.
No.
Okay.
No. I mean, the nice thing about these alternating series is that the AST is super fast.
Yes.
And then to test whether it's whether it's conditional or absolute, we just erase that.
Mm.
So it's not too crazy.
Yeah, and then you just do what we've already learned before.
Yeah, and then we're applying what we already know. Yep. All right, let's go ahead and take our 10-minute break.
Don't you just love infinite series that converge to a negative number?
Sure.
Especially when that number is minus 12.
They're in series.
Alternating series. Okay, let's do this one. So alternating series. Now the switch is not called out here, but you can see that there's a -1 to the k there. Oh, and notice that this one starts with a negative term. Right? The first term is negative. So if this series is finite, it's going to add up to a negative number. What kind of series is that? Geometric. Does it converge or diverge? Converge? Because R is less than 1 in magnitude? Yep. So this is geometric. So just side note here, R is equal to -1/3. And the magnitude of R is less than 1. So therefore we have convergent. So we know it converges. Now we would want to analyze whether it converges absolutely or not. So we have a convergent series. It's alternating, so we have a converging alternating series. The next step then is to test the series of absolute values. So the series of absolute values, all we do is get rid of the minus. And when we get rid of the minus, we have that series. So that's the series of absolute values. So these are absolute values. Does this series converge?
Yeah.
Yeah. Once again, R has a magnitude that is less than 1, which means convergent. So the convergence up top, then, this can be classified as what kind of convergence?
Absolute.
So this is going to be absolute convergence, not conditional convergence. Now this is a geometric series, so we can also tell what it converges to. So we know that for a geometric series, the sum is equal to
A over 1 minus R.
A divided by 1 minus R. What is A?
Or 1/3.
Negative 1/3.
Negative 1/3. Plug in the initial index.
To be honest, I was looking at the blue writing.
Yeah, that one has a different sum though, right? So we can find the sum of that series too. And then this is 1 minus R. So we get that. So if we multiply everything through by 3 just to clear out the fractions instantly, this series converges to -1/4. And if we did want to find the sum of this other series for whatever reason, we could find the sum of this series too. What would the sum of this series be?
0?
0?
Well, no.
A sum of a series of positive terms? So this is going to be A, which is 1/3, divided by 1 minus R. We're going to get that. And then same thing. This is 2/3. Flip it over. Are you going to get 1/2?
0 plus 1/2 is what I meant. Just kidding.
0 plus 1/2. So obviously the series converged to different values because that has a positive R, that has a negative R. But that series we're going to say converges absolutely.
Did you also look at the series and say 1/3 would be the absolute value of that?
Mhm.
And then if you say that converges, you could say, well then, the alternating must converge.
Absolutely. So if you came here first and you concluded that the series of absolute values converges, that implies that the original one converges also. So you could definitely use that logic. That is totally legit. Legit. Where are we? Oh, we get to go to our new test soon. Okay, so absolute and conditional convergence, determine whether the following series converge absolutely, converge conditionally, or diverge. So this is an alternating series, and the one that's going to be on the test, you will be able to show by alternating series test comfortably that it converges. This one's a little bit of a hassle, but let's at least start, let's talk about it as we go. So to show the AST, to show that this is a convergent series, first we take the limit of a sub k, so we're going to take the limit of this as k goes to infinity. And when you have a square root in one part of the fraction but not the other, the simplest way to deal with this is to put a square root in both places. So we're going to put a square root on the top, but then square the top, so that we can then combine the square roots. And that's going to give us a nice, easy way to compute the limit. So here we'll have k to the 4th over k to the 6 plus 1. And what is our limit? 0. Power on the denominator is bigger, so that limit is 0. Now, to show that these are decreasing, it's a little bit more work. So we want to show that going further out into the series, the terms are getting progressively smaller in magnitude. There is a way to show decreasing from calculus 1. The derivative being negative. Right? If you have a function, and that function is going down, the tangent lines are sloping in the negative direction. So you can show that a function, which a sequence is an example of a function, we can show a function, in this case a sequence, is decreasing by looking at the first derivative. So the inequality thing here gets super messy because remember, k plus 1, you'd have to put in a k plus 1 for this k and then square it. This k plus 1, you'd have to raise it to the 6th power. It'd be pretty awful. So what we are going to do is this. So we're going to consider, let me ask you this question also. If a function is decreasing to 0, do you think the function's square roots are also decreasing to 0? Like if you're imagining this sequence going down to 0, and now you take the square root of that number, 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 that's also decreasing, right? So the point here is that we could consider the square of this function. We could consider y equals k to the 4th over k to the 6 plus 1 instead of that square root. If we leave the square root in there, the derivative with that square root is going to be a total headache. But it would be sufficient if we consider this. If this function is decreasing, then the square root of that function is also decreasing. Okay, so how do we show that this is decreasing? We're going to take its derivative. That's a quotient, so we have to use the quotient law, quotient rule. So we do denominator times derivative of numerator, low d high, minus high d low. All over the denominator squared. Yeah, it can be a little tedious for sure. Let's see, let's get some like terms going here. So we have 4k to the 9th in the numerator. Plus 4k cubed, minus 6k to the 9, all divided by, let's leave that alone for now.
Wait, k to the 4th or k squared?
We squared both top and bottom. We're looking at the k to the 4 over k to the 6 plus 1. So if you have a sequence and you square all the terms, it's going to go to the same place. If the original sequence is going to 0. Okay, so do you see that we get negative 2k to the 9th plus 4k cubed over this? You agree the denominator is positive, right?
Yep.
So over a positive number. Isn't the numerator negative? This term, k to the 9th, dominates that numerator. So whatever its coefficient is going to dictate whether that numerator is positive or negative. So the denominator is positive, the numerator is negative, this is less than 0, therefore decreasing. So that tells us then that the series converges. Let's move this thing down a little bit. So our conclusion here is therefore we have a convergent alternating series. So by the AST, that converges. So now our question is, does it converge conditionally, or does it converge absolutely? Question?
So if absolute convergence means the alternating also converges, why
Yep.
don't we always check whether the absolute converges? Why do we check the alternating?
Because it becomes a headache if the absolute doesn't converge, and you have to go back and do the other thing anyway. Usually the alternating series test is really fast, usually. And so if you have to do it anyway, in at least half the cases you have to do it anyway, that's kind of, it doesn't save you a lot of time. All right, let's take a look at the series of absolute values. So series of absolute values, we get rid of the switch. So it's going to be k squared over the square root of k to the 6 plus 1. And this technically starts at 1. All right, so how do you think we're going to get at whether this series converges or diverges?
Integral test.
Ooh, gosh, that's bold. I say there's a better way than the integral test. Blah, blah, blah. Mumbo, mumbo.
Limit comparison.
Comparison test. Because we know that polynomials are dominated by their leading term. So if we ditch the 1, we might be able to get a good sense of what's going on. So this is our a sub k. Let's choose as our b sub k. Let's see. When we choose this b sub k, we get rid of the 1, and we're going to have k squared in the numerator. We're getting rid of the 1 in the denominator. We can take the square root of k to the 6. That's going to be k to the 3. Doesn't this all reduce then to just 1 over k? Which diverges. So the series b sub k diverges. Why? Because it's a harmonic, or you could say it's a p series with p less than or equal to 1. So we suspect, of course, that the other one diverges. So here's how we're going to use our comparison test. So first we always go direct comparison first, just to see if we can show it. So we would want to show, so here's our a sub k, here's our b sub k. If the b sub k series diverges, do we want to show that the a sub k series is bigger or smaller? Bigger, because bigger than diverging will diverge. So if we can show that that's true, we're golden. So the a sub k series, we put it here. And if this doesn't work, if the inequality doesn't hold, we just go to limit comparison. So this is going to be k cubed greater than or equal to the square root of k to the 6 plus 1. We square both sides. And is it true or false? False. So we're going to go to limit comparison test. So bummer, that's false. So we have to go to limit comparison test. So let's go to limit comparison test. So we're going to take the limit as k goes to infinity of a sub k over b sub k. So limit comparison test says take the limit of the ratio of a sub k and b sub k, and, well, let's do that first, and we'll talk about what the conclusions are for the limit comparison test. So we're taking our a sub k, dividing by b sub k, which means multiplying by the reciprocal of b sub k. So we're going to take the limit of k cubed over the square root. So we get that. And then we do our clever little trick. We square and square root the numerator so that we have one big square root and we can combine the guts. We can combine what's inside.
Could you also multiply the numerator and denominator by the square root of, by 1 over the square root of k to the 6th?
Yeah, it's going to get a little messy if you do that, but you could do that. And what does that limit equal to? So now we have to remember our conclusion. It's a positive real. So if we take the ratio of a sub k and b sub k, take the limit, and we get a positive real, that means they're linked. That means they are going to behave in the same way. They both converge or they both diverge. And since the b sub k series diverge, therefore both diverge. So now we know that that series is a divergent series.
So if the limit comparison test gives you 0, then you have convergence?
Is 0 a positive real?
Sorry.
If you get 0, that's one of those special cases. If you get 0 or infinity, that's one of the special cases which we're not really looking
Just then
at.
if we got 1, then 1 is in positive reals though.
It's positive real.
So then why doesn't that converge?
It means that the series do the same thing. If you get a positive real, it's kind of like saying that the series are, 1 unit apart, but they're going in the same direction, whether it's towards convergence or divergence. I guess saying it's 1 unit apart is probably not the best. If you get a positive real, it means they're linked. Maybe they're going to different places, but they're both going to some limit.
And I don't know, like, question on the test is long.
No, this one's especially long. This one's a little longer than
It's evil.
this one's a trick.
It's an evil test question.
It's not a treat. Okay, so what is our final conclusion?
Conditional convergence?
Yes, conditional convergence. So all of that stuff in blue right down here leads us to make our final conclusion of conditional convergence. So the original convergence was just regular old convergence, pluses and minuses doing what they do. And now we know that if we take absolute values, we're going to get divergence. So the original convergence is classified as conditional. Okay, let's look at this one. So once again, the alternating series test, just to show that this series converges in the regular sense. So alternating series test, the limit of 1 over natural log of k as k goes to infinity is? What would that limit be?
0.
So the denominator is growing and growing, the numerator is staying fixed at 1. If the denominator is growing without bound, the fractions must be shrinking to 0. That checks. And then we want to show that the sequence of terms is a decreasing sequence. If we can show that it's a decreasing sequence, we'll be done. We put in our 1 over natural log of k here, 1 over natural log of k plus 1 here. Don't know. That's what we want to show. And if we do our little cross multiplication gig and then exponentiate both sides, we end up with a true statement. So that's true. So that checks. So now we have both pieces of the alternating series test affirmative. So that means that that is a convergent series. That alternating series converges. And then we want to classify that convergence. And it's going to end up being conditional. So when we look at the series of absolute values, 1 over natural log of k, we know that that series diverges. We already did it. But what is the technique to show that it diverges? This denominator goes to infinity, but it goes to infinity even slower than k goes to infinity. So if we compare this to the harmonic, so if we do this, so then our b sub k series is going to diverge because it's the harmonic. So we've got this diverging harmonic. What would the direction of the inequality be? We want to say, okay, well, the series we're analyzing, that's a sub k. We would want to show that it's bigger or smaller than b sub k if b sub k is a divergent series. Bigger than diverging diverges. So we want to show that. And so we already went through this last week. We get to here, and we talked about looking at the graph. You could also look at the difference and take its derivative and show that the difference between the two is increasing. There's a few ways to show it, but
It'd be 1 is greater than 1 over k, right?
we have that. K, y equals k, y equals ln k, y equals k is always bigger. So that's true. So if this is true, therefore, what is our conclusion here? Therefore, both diverge. So both diverge. So then what is true about this convergence then? Got to be conditioned on those minuses. So the series of absolute values diverges by comparison test. So that means the original convergence is conditional.
Could you just exponentiate both sides of that k is greater than epsilon k? Would that just be another way to do it?
Yep.
Okay.
Yep. So if you exponentiate both sides there, then you end up with an e to the k greater than k. So then you're just looking at this graph instead. That versus this.
Yep. Okay.
Definitely.
Sweet.
Either way.
Should you put the graphs on to show?
You can do that. You can do. I mean, it's kind of by this stage in the game. This is totally. I assume that you know that. Maybe that's not the best assumption, but. Okay, let's go ahead and we have that one other one we need to get to still, but I want to make sure we start on. We want to get through these ratio and root test stuff. So we still have one question from the before that we're going to get to eventually.
Just put it off on
Put it off until
It's the last thing we do in class before the exam.
last thing we do before we leave on winter break. It's just one example.
Just right after the final exam. Oh, and before you leave.
For no credit. All right, so here we're going to deal with two tests, our final two Tests 9 and 10, I think if we counted to 10, I think we counted to 10 earlier. So our final two tests, they are very similar to each other, and they are probably the most important two tests because we are going to use them in the next chapter when we talk about infinite series of functions, aka power series. You use the root or the ratio test. So root and ratio is where we're at. So the ratio test says this. Let's suppose we've got an infinite series. Can have positives, can have negatives, doesn't matter. We are going to take the limit of the ratio of absolute values. So as soon as we take that absolute value, you should sort of be thinking, well, aren't we finding conditional and absolute convergence then? And yeah, the idea is that if we take absolute values, we are finding absolute convergence. Okay, so let's see. So we take this ratio, take the limit, get an R value, and dang, they're using the letter R, which should remind you of what type of series? Geometric. And the conclusion of the geometric series, oh, it's the same. Less than 1 converge, greater than 1 diverge, equals 1. In this case, it's inconclusive if it's equal to 1. Okay, so that tells us that we've got this new test, but it behaves a lot like an old test called the geometric series. Now, why might it act like the geometric series? Well, let's take a look at this limit. If this is true, and then you consider being way the heck out in the tail, this says that way out in the tail, you have this setup. So, out in the tail. So way out. Big old K's. Way out there. Well, then let's cross multiply here. So in the tail, not really cross multiply, multiply both sides by absolute a sub k. So out in the tail, the next term is r times the prior term. And that repeats itself. R times the prior term, r times the prior term, r times the prior term. Right here. R times the prior term, r times the prior term, r times the prior term. And what type of series is that? Geometric. So the ratio test is basically a glorified geometric series. So out in the tail, the series is going to act geometric. And so that's why we end up with the same conclusions that we had from the geometric series. Bigger than 1, converge. Less than 1, diverge. Equal to 1, inconclusive. So let's try this little ratio test. And let me point out, see that factorial? Whenever you see a factorial, the ratio test 99% of the time is going to be the best way to go. You will see.
I was thinking you can use ratio test without just saying growth rates.
You can use a ratio test, right?
Well, we couldn't
So-
use growth rates because there's a switch.
So the ratio test says take the limit of the absolute value of the ratios. So that immediately gets rid of the switch. Let me just write this down first. So this is going to be limit a sub k. We're taking the absolute value of a sub k. Oh, I'm sorry. That should be a sub. What should go? What is the ratio supposed to be?
A sub k plus 1 over
A sub k plus 1 over a sub k. I started to do the, what's it called? What's the ratio?
limit comparison.
Yeah, the comparison test, limit comparison test. So here we are going to be looking at ratios of consecutive terms. So this is a sub k plus 1 with an absolute value. So the absolute value just gets rid of the minus. So a sub k plus 1 over a sub k. And now we're dividing by a sub k, which means multiply by its reciprocal. And I'm just going to put big absolute value bars just to emphasize, even though we already took the minus away, we don't need the minus anymore, because that's what the absolute value will do. And this is what's so cool. Don't those factorials just wipe each other out except for a k plus 1 in the bottom? Right? K plus 1 if you have 5 factorial over 6 factorial, you would get 1 over 6. Right? There's one extra factor here. K plus 1 factorial is k plus 1 times k factorial. So that will simplify tremendously into just a k plus 1 in the denominator. And so that's why the ratio test is so nice whenever you see a factorial, because you know the factorials are just going to vanish. And then how many 2's are left? And where? How many 2's are left? Just a 2 in the numerator. Right? Because we have one extra 2 up top. We have k of them down below, but up here we have k plus 1 of them. So there's one extra 2 up top. And what is this limit? 0? Wait.
What did you do?
Where'd the math go?
Why is it k plus 1 factorial on the bottom when it says if a sub k plus 1 over a sub k?
You can't, how do you cancel the 2's like that?
Okay, hold on. Let me answer, Harrison, your question first. So a sub k plus 1 means take this and put a k plus 1 in each place.
Yes.
So that, and then we divide by a sub k, which means multiply by the reciprocal.
Yes.
And then this is 2 to a power of k plus 1.
Okay.
So there's one extra 2, so we're left with the 2 in the numerator. K factorial has one less factor than this, so we're left with the k plus 1. But this means it's inconclusive. Right?
I thought it was only if you equal 1. It's
Yeah. Oh my
It
God.
surely converges absolute.
Yeah, I'm sorry. I was thinking in my mind that 0 was inconclusive. Where did we have a 0 as inconclusive?
divergence test.
Divergence test, yeah. With the geometric series, remember that if r is less than 1, you have convergence. If r is greater than 1, you have divergence. And if r is equal to 1, that's where it's inconclusive. I saw the 0 and I was thinking, oh, there's 0 conclusion.
So you get your test mixed?
I got my test mixed up. Oh my gosh. So sad. Less than 1, therefore. Oh my gosh, I panicked. I was panicking. I was like, wait, it can't be inconclusive. That's what's so nice about the ratio test. It's usually very fast. It's usually just a few steps.
I'm just still lost on why there's only 1 2.
If you have 7 2's in the numerator and 6 2's in the denominator, how many 2's do you have left? 1. If you have 7 up top and 6 below. So here you have k below. You see it? The other way to do it is that if you have exponentials with the same base, you subtract the exponents. K plus 1 minus k, which is 1. Yeah. All right.
And for the factorials, the idea is that k plus 1 factorial simplifies to k plus 1 plus k factorial.
So k plus 1 factorial is k plus 1 times k factorial, yes. Just like 6 factorial is 6 times 5 factorial. All right, let's try another one. So ratio test here. So we say limit. K is going off towards la la land. Absolute value of a sub k plus 1 over absolute value of a sub k. So limit.
Can we just use one big absolute value
Yep.
bar?
Mm-hmm. So a sub k plus 1, we're going to replace all those k's with k plus 1. We don't see any negatives in here, so we can actually forget the absolute value bars at this point. So there's a sub k plus 1. What are we going to multiply by? Reciprocal of b sub k, so we just flip, reciprocal of a sub k, so we just flip it. All right, Austin, how many 4's are left and where?
1 on the denominator.
Yeah, exactly. Does everyone else see that? 1, 4 left in the bottom?
Yes.
So we have 1, 4 left in the denominator. Oh, and actually, this is a little different. So this k plus 1, we have 1/4. And then let's combine the k plus 1 and the k like that. So, or maybe, no, let's write it a different way. I want to write it a different way. You can write it this way, but I want to point something out. You could just square this out in this case since it's so easy. Let's do it like that. So what is this overall limit? What was that? 1/4. The overall limit's 1/4. The limit of this fraction part here is 1. And we could have done it the other way too. If you have k plus 1 over k, quantity squared, k plus 1 over k goes to 1, 1 squared goes to 1. Doesn't really matter. Here I just sort of want you to think about if you have polynomials with matching powers, you can ignore these insignificant terms. So this is 1/4. This is less than 1. Same conclusion as the geometric series, less than 1 converges. So there is our. And to be even more precise, if you have an alternating series, like this one is alternating, this convergence is absolute. So if you have minuses in there, you can also include this. It didn't ask us to do that, but we know that convergence would be absolute because we took absolute values. All right, let's do another. Yeah.
So if you do like a growth rates test on it, and if it's divergent, you don't have to do this ratio test, but if it's convergent, you want to do ratio test to make sure, correct?
I think so. You said say the first part of your sentence again.
Can't you use growth rates on the problem we just did?
But if you use growth rates
It would be inconclusive if it shows that it's convergent.
on this one here,
Yes.
all growth rates does is show us that this goes to 0.
Yes.
Doesn't show us how fast it goes to 0, whether it converges or diverges.
Okay.
But it gives us the insight that it might converge.
Okay.
Whereas if this was flipped over, growth rates would say that has to diverge.
Yes, so that's what I'm saying, is if we use growth rates first on this and it shows that it diverges, we don't have to do this.
That's right.
Okay.
That's right.
Okay, good.
So that's essentially the divergence test.
Yes, the
Yeah.
divergence test, okay.
Yeah. That's.
Which is the test you always use first.
This is a test we should at least always be thinking about in our mind.
Yeah.
All right, so let's set up this one here. Limit as k goes to infinity. Again, we want absolute value of each of these. So first we're going to find a sub k plus 1. So we're going to replace all the k's with k plus 1. We're going to ditch the switch. Absolute value takes away the switch. And then we're going to flip a sub k. So we have that. How many 7s and where? 1 in the top. So we're going to have 7k squared over, if we FOIL this out, what do we get for our limit? 7. And this is bigger than 1, therefore diverge. So geometric series says bigger than 1 diverge, less than 1 converge, 1 is inconclusive. So this is one of those types, when you look, 7 to the k is exponential.
Yeah.
That's polynomial, so the limit of this is going to be 0. Excuse me, the limit of that's going to be
Divergent.
diverging. It's going to be infinity if you took the limit of this, if you get rid of the minus.
And on the test, if we use the power rule instead of doing this divergent, we don't have to, or growth rate, sorry.
Yeah, you just have to pay attention what the instructions say. If it says use ratio test, use the ratio test.
Okay.
All right, let's try this one. And anytime we see that factorial, that is a real strong indication that the ratio test is going to be the way to go. Even though on the test I'll tell you just to try to keep you from falling into a rabbit hole. So once again, we're taking absolute values, so that minus right there, the switch, we can ditch the switch. Don't need it. So we're going to have k plus 1 factorial over k plus 1 to the 6. Start foiling, Austin. We get that. K plus 1 in the numerator. Is everyone okay with that? So the factorial business. So we have a k plus 1 up here. Now, this numerator, we have a k to the 6. Down here, remember that polynomials are driven, they're dominated by the leading term. So if we're taking a limit at infinity, we don't care about the 5th order term, the 4th order term, the 3rd order term, the 2nd order term, the 1st order term, the constant. We don't care. We can just reduce that to k to the 6. We can just reduce it to its dominant term. And the justification in your mind is that, well, if you divided everything by k to the 6, over here you'd have a 1 over k to the 6, and then each term would have a bigger power in the denominator. You'd have all these little terms going to 0. Right? So if you have a polynomial over a polynomial, only if you're going to infinity, you can ditch everything except the highest power. And then what is this limit? Infinity. Therefore, diverge. You could also use the divergence test here. The limit of this is not 0, so therefore it diverges.
So would there also be a situation where if it equals negative infinity, it will converge? Since that goes with the, say, oh, never mind, sorry. Yeah, I see.
Yeah. We're always going to take those absolute values, so. And then there was one test left.
This is the last one, just the second one.
Sure.
Just how did you know that you could ignore the plus 1 part? Or is it because of how like when we square it, we only take the biggest one, so
Yeah,
to
it's
whatever power, we just take the biggest one?
It's that idea, like if you have k squared, and down here you have k plus 2 quantity squared. If you were to FOIL this all out, like in this case it's simple to FOIL it out, you have this. And now what we usually say is, oh, divide by the highest power of k. And so each of these little terms down here, when you take the limit, these are all going to go to 0. So it's sufficient when you have a limit at infinity. If you have some expression raised to a power, you can just you can see what the dominant term is. So that would be the dominant term. So it's okay to just basically erase the 2 and square only the k. So here, erase the 1 and only raise the 6th power to the k. So that dominant term is always going to dictate what the value of the limit will be at infinity, not elsewhere. Final test, the root test. So the root test, we're going to take the kth root of the kth term. And notice the conclusion. Same as the geometric series. Less than 1 converge, greater than 1 diverge. And then we have an inconclusive if rho is 1. Greek letter
That's not a P.
R. It's a rho. Row, row, row your boat.
Oh my gosh.
Okay, so once again, hidden geometric series. Well, if that limit is there, if you go out for large K, so you go hang out way into the tail, this means that rho is approximately equal to the kth root of a sub k. Okay, if it's equal to the kth root of a sub k, you can raise both sides to the kth power, and here is what we have. This says that a sub k is about equal to, so out in the tail of the series, a sub k is about rho to the k, which means a sub k plus 1 is about rho to the k plus 1, which means a sub k plus 2 is about equal to rho to the k plus 2. Once again, geometric series with a common ratio of rho. So the root and the ratio test have embedded geometric tails within them. And we know that you only need to consider the tail when you're considering the convergence or divergence of a series. So again, geometric. So our conclusions are the same. So let's try good old root test. This brings up our old friend, the log limit thing that we've done a bunch with the divergence test. Right? Normally we would look at this and say, oh gosh, this one is not exactly indeterminate, but normally those ones that were indeterminate of the form 1 to the infinity, this is, if you took the limit to the inside here, you would get -2, so it's not quite like that. But you can imagine some of those ones we could use the root test, because watch how fast the root test comes in. So we're going to take the limit as k goes to infinity of the kth root of the absolute value of a sub k. So we just get rid, in one fell swoop, we get rid of that outside power. So this is going to be the kth root of all this, and we're absolute valuing that. So we get that. Everyone follow that? The kth root of that? The kth root will undo a kth power. So we just get the base, but remember that we're taking an absolute value, so that's why the minus goes away.
And if you're using this root test, I'm assuming we're only going to use it when it's something like to the k or anything, basically everything to the k.
Yeah, if there's a power on the outside, that's going to be the classic time for the root test.
All right.
And notice how fast this is. So this limit is 2. Again, same reasoning that we've used before. We can just consider the dominant terms. Ditch that 1. Limit is 2. This is bigger than 1, therefore diverge. Yeah, the root test and ratio test can be pretty darn fast. Here's a great place to use the root test if you have power towers. So power tower, root test, factorial, ratio test. Okay, so same setup. We're going to take the kth root, absolute value of a sub k. So what is the kth root of k to the k?
K over 2.
So we're going to end up with k over 2. Everyone okay with that? Everyone okay? Limit is infinity. So therefore, diverge. It also diverges by the divergence test. The limit of a sub k is not 0. But the root test gives us a nice quick conclusion. It's not too bad. Not too bad, this root test thing. Now, so, k to the k, kth root of k. So the question is, what is the limit of the kth root of k? So that sequence looks like this. This is what the sequence is. 1, root 2, cubed root of 3, 4th root of 4, 5th root of 5, 6th root of 6. And I graphed it earlier today just to sort of give you a visual. I just did it today, Daniel.
Oh, okay.
I'm always adding stuff as we go. So what do you think, based on the graph, that the limit should be?
1.
1. But that's not intuitive. When you look at that, not obvious that that limit should be 1. What do you think, what technique do you think we're going to use to get at that? The root test tells us whether a series converges or diverges. If we just want the limit of a sequence, so there's no series yet here, we just want the limit of this sequence. So we see our sequence terms getting closer to 1. What technique have we used repeatedly when things are weird with exponents? There's a technique that we use to bring down the exponent, log limit. So if we let y equal x to the 1 over x, and then we take the log of both sides, well then on the right-hand side we can bring down the exponent. And then we take the limit of both sides, and the limit can jump inside. And then on the right, when we take the limit, we want to put it in a L'Hopital form. And so there is our L'Hopital form instantly. We didn't have to do too much. We just have to move that x in the denominator. Now it's in L'Hopital. Right? It's infinity over infinity. It's indeterminate. So then we're going to use L'Hopital's rule. This is infinity over infinity. So L'Hopital's rule says take the derivative of the numerator and divide it by the derivative of the denominator. And as x goes to infinity, what is that limit? Zero. And then we have to exponentiate both sides to get rid of that ln that's floating on the left-hand side. So the limit of y as x goes to infinity is e to the 0, which is 1. So this limit is 1. So k raised to the kth power as k goes to infinity will approach 1. Not obvious, but it's going to be very helpful. So here, let's take a look at the retest. So with this one, if we take the limit as k goes to infinity, kth root absolute value of a sub k, this is going to be the limit of the kth root of k over e. So if we take the kth root of the numerator and the kth root of the denominator, the kth root of e to the k is e, and we're left with this. Now we know that the limit of k to the 1/k as k goes to infinity is 1. So we get an overall limit of 1 over e. That's less than 1. Therefore, converge. So that 1 over e is what they call rho, Greek letter r. Just like the ratio test, just like the geometric series, if r is less than 1. Weird scenes inside the gold mine. So here's another classic root test. So here, when we take the kth root of a sub k, we have to be a little bit careful here. So we are taking the absolute value. The k on the outside, obviously that part disappears. But what about 1 minus 5k? So this k is going to be gone, right? That's going away. But we're taking the absolute value. Is 1 minus 5k positive or is 1 minus 5k negative? K starts at 1 and gets bigger. So it's always negative. If you have two numbers subtracting to a negative and you just flip them, doesn't that make it positive? Right? So 5k minus 1. So when we reduce this, this is how we will take the absolute value. So the absolute value of a minus b is the same thing as the absolute value of b minus a. We're just going to choose the positive direction. What's that look for? Nothing. Do you agree if 1 minus 4 is negative, if you flip them, 4 minus 1 is then positive?
Oh, it wasn't.
Oh, it wasn't about that. Is everyone okay with that? All right, so the k values here are going from 1 up, so this is negative the way it sits. So if we flip it, it's going to make it positive. What's the limit of this? So once again, the power on the k's match, so we can take the leading coefficients. So that's 1/5. And this is like the geometric series, so less than 1, therefore converge.
So wait, did you just multiply the fraction by -1 to get it to do that? And then use the absolute value to get it to go away?
To get to this step here,
Yes.
I used this fact. So I use the fact that a minus b's absolute value is the same thing as the absolute value of b minus a. And so the idea is to pick whatever, this is going to be whichever one's positive. So if a minus b happens to be positive, then this would be a minus b. But if b minus a is positive, only one of them is going to be positive. Then you pick that one.
Just jack around with it.
Yes. Yeah.
Absolute value. Okay.
Yep. So the absolute value of this is going to be the same as the absolute value of 5k minus 1. But 5k minus 1 is always positive. So that's absolute value, we don't need it. Yeah. Algebra. Algebroni. Choose a test. What do you think would be a great test for that first one?
Ratio.
The first one.
I like your thinking. Ratio test. Anytime we see a factorial, but now let's see if you can think about this correctly. So we're going to do a sub k plus 1 over a sub k, absolute value. We don't need the absolute values here because everything's positive, so we can already forget about that. But this is going to be k plus 1 factorial all cubed divided by 3k plus 3 factorial. Right, the k is being replaced with a k plus 1, and the 3 has to distribute. Then we're going to flip, and we're going to have 3k quantity factorial, and then k factorial cubed. So does anyone have a question on that first part? So a sub k plus 1, that's the part that might be causing you grief. So then, okay, here, I'm going to rewrite this as k plus 1 times k factorial, and then distribute that power of 3 to each of these. So that's the first thing. Top left corner there, k plus 1 factorial is k plus 1 multiplied by k factorial, but we've got a power that's got to affect each of those individual factors. And then let's keep this one as is. There's nothing to peel off there. Now down here, I see a 3k quantity factorial. Can't I rewrite 3k plus 3 quantity factorial? Can I start popping terms like this? Do you see that? So here, that is that. Right? You can pull off, it's just like 6 factorial is 6 times 5 times 4 factorial. or 6 times, 5 times, 4 times, 3 times 2 factorial. You can put the factorial wherever you want. So you do repeated subtraction of 1 to get your consecutive factors, and then drop in the factorial wherever it makes sense. And then we still have that one other factor in the bottom. So we have, let's see, what else? We have a k factorial quantity cubed. Now we're going to have some cancellation. K factorial quantity cubed, k factorial quantity cubed. A 3k factorial. 3k factorial. Now we're in that polynomial limit at infinity land again. What is the dominant term in the numerator? What's the highest power of k? That k plus 1 cubed. If you were to cube it all out, you would get k cubed would be the dominant term in the numerator. How about in the denominator? We have this 3k, we have this 3k, we have this 3k. Isn't the first times the first times the first, won't that be the highest power of k if you were to, right? So what is that going to be?
K cubed. Well, 9k cubed.
27, they know that's the number. 27k cubed. So we can do this, and then our limit will be at 1 over 27, which is less than 1. Question? So this is going to be converge.
So there's two.
And because we did an absolute value, you could say it's absolutely convergent, but these are all positive terms anyway, so convergence and absolute convergence there's no distinction between the two if everything's positive.
That one was pretty long. Would we have something similar to that length?
This one was pretty long.
I mean, longer than.
This is medium.
Yeah.
This one I think is reasonable.
This one
No.
I'll put 3 problems on the test, at least.
What number?
5.
Should this be number 5?
Yes.
Yes, that exactly. Everything.
I would, if I like memorize exactly what the answer is, I write it down.
You can put it on the exam, half us are forget, so.
I know. I have done that before. I have done that before. I've done the exact question in the review, and I'm like, oh, there's no way people are going to miss this. We just did the exact question.
Less than.
No, I noticed it on the last test I did.
There was some that were,
Yeah, it was e to the x inverse tangent, and
Yeah.
it was on one of the other
I know, yeah.
test questions.
That one was, I did do that one intentionally. There's,
So we'll get to 10.5 next time.
yeah, we'll finish that question next time. Because now we have one question from this section and one question from that section. How about this? You guys try to do it, and we'll do it together on Thursday.
It's like an infinite series.
It's like a series that never ends. It goes on and on and on and on. It goes on forever. I'm very happy that that toolbar showed up at the bottom.
Yeah, and then we also have this also as well. Well, yeah.